I'm very confident because my all-nighter teammate just got an 8.6 before he did it. So let's start. Okay, so this is number 11. I'm also an investment bank. I have no knowledge of program structure. So the problem statement reads: connect two metal balls with an elastic band, then twist the elastic band and put the balls on the table. The balls will begin to spin in one direction, then in the other. Explain this phenomenon and investigate how the behavior of such a pendulum depends on the relevant factors. Our three focuses will be: 1. Why do the balls spin in such a manner? 2. How do the relevant variables affect the acceleration and the stability of such a system? And 3. What are the special phenomena that can be observed in this system? First, we'll begin with the phenomena investigation, where we'll then have a demonstration with initial assumptions. Then we'll have a provable theoretical model with our free body diagrams and equation of motion. We'll then move on to experimentation and discussion, where we will perform error analysis and discuss the limits of our theory, and then we'll conclude with some future work. So the key components of this observation is first a rubber band that is connected on both ends to identical metal balls. We also have a constant surface with controlled friction. These frictions. So here you see initially the balls spin outward, and then they decrease in radius, and then they start spinning in the opposite direction with the balls radius changing increasing too. So here are our assumptions and some little insights. So the rubber bands are constant strength throughout. We consider the rubber band having a spring constant. If you have questions about this, we have some extra slides at the end that shows this. Rubber bands are kept at a constant temperature because, as you know, the thermodynamical properties of rubber bands assume this. And we'll also assume that there is no net horizontal force exerted on the system, and which means the center of mass of the system does not move in any direction. We also assume that there is no vertical movement because the floor and the wall are smooth. Here's our theoretical model, and here are the variables. So here's our acceleration kinematics diagram. First, we define the r hat direction to be the vector from the center of mass of the two balls. So another ball will be over here, so the origin will be the center of mass. So r hat will be the vector from the origin to that ball. Theta hat will be the instantaneous tangential velocity vector. And v will be the vector sum of those two vectors. Yes. So we have theta hat, which is that will be equal to negative sin theta x hat plus cosine theta y hat. We also have r hat is equal to cosine theta x hat plus sin theta y hat. We can differentiate this and differentiate that. Note how these very beautifully cancel out to have theta hat and negative theta r hat. And we have v equals r d theta dt theta hat plus dr dt r hat. And you can do some Chamberlain's and Hawkes rule to get the acceleration. So here's our dynamical system. So here we define our variables and we have our free body diagram. First we have our first two force equations. So the force equation in r hat direction reads the force of the tension force plus force of friction K will be equal to mass times the acceleration in the r direction. And note how we derived in the previous slide that the acceleration in the r direction will be that. The second equation is basically the same thing except it's for the theta direction. And our third equation actually is the torque equation, where K delta V will be the torsional torque exerted by the rubber band on the ball, and that will be the static friction force that also comes with the torque. And we can basically rearrange those equations of motion to get these three tested equations of motion. Note that these equations are coupled, so instead of solving them analytically, we solve them numerically using Python. So basically, we wrote this program that will test this. Note that there are some internal variables that are hidden inside of those parameters shown because they represent variables that impact the motions. Changing those variables, you can get your corresponding graphs directly. First, we have the angle versus time, which resembles a kind of a dance harmonic motion. We also have a radius versus time. Note that for the radius versus time, it does reach an equilibrium due to the there's a kinetic friction force in the r hat direction. Whereas in the theta hat direction, there is no opposing kinetic friction force. So that is why the radius versus time will stop. So here we move on to experimentation and discussion. So here's our experimental setup. First, we have a plan to control the turns of our balls, so that every time we can control how much it turns. Here we have two out of a variety of balls with different masses that we test. We have two out of many varying rubber bands. In fact, we use more than rubber bands. We also use kind of the robotics tubing that has also different K and torsional constants. And here is our system of interest. And this, for example, is a ground. It's one of many surfaces we use, such as wood, TYPT, which is an extremely low friction surface we use to test for rolling without slipping. And also, we have a tripod with our camera on top. So here is our methods of analysis. We basically have our two balls over here. We track both of the balls, so then we can find the center of mass. Using that, we can finding the radius of the rubber band is pretty easy, but the thing with finding the angle is you have to use an arctan function. So we're going to have a ball like this and like this, and to find the angle, we'll find the difference between y and the difference between the x, and find the arctan. But the problem is with the arctan function that after every 360 degrees, it resets to 0. So our graph will basically shift down every 360 degrees. So we had to build our custom Python function to add that 360 degrees every time it goes a full turn. So our first experiment involved verifying the proportionality between omega r and n. So this is derived from our kinetic energy equation shown over here. Note that there are two rotational kinetic energies. One is the rotational kinetic energy of the system rotating like this. But also there's another kinetic energy of the balls rolling by themselves. So this will be the balls and that will be the system. And after some trivial manipulations, you can get omega r is proportional to n, which we already defined as the number of turns you give the ball. So here's our experimental comparison. You can see that the graph appears to show a linear line, and that all the data are within 2 standard deviations of the graph, which shows that the empirical data basically supports our theory. Our second experiment involves experimenting with mass. Note how we don't have an explicit function of maximum angle past equilibrium versus mass. Because as we mentioned earlier, we couldn't solve these questions analytically, we use the Python program. So we do that by approximating, by changing the mass in a numerical program and finding the largest value is spins past equilibrium in that program graph. So, and here are some sample points plotted over here. Note that the mass of the rubber band is negligible because it accounts for less than 1% in the calculation. Next. So here is, we actually have 1, 2, 3, 4, 5, 6 different masses we tested, and we have our 6 corresponding Python numerical solution points over here. You can see that almost all of the data points are within 2 standard deviations of the theory, which means that there's no statistical evidence to reject our claim. However, we must note that this theoretical approach may only be accurate for certain parameters because, we don't have a specific equation. Instead, we have to solve it numerically through Python. And here are the most important graphs. Angle versus time theory graph, which we already showed earlier in our Python slide. And here is the comparison between our experimental graph, which is shown in red, and our blue graph, which is the theoretical graph. So here's the error analysis. You can see that the R-squared value is 0.7, which generally is not considered to be very high. However, I don't think R-squared value is a very good way to measure the accuracy in such an experiment or for such a graph. Because you can see that our graph basically still qualitatively agrees and it resembles the overall shape. In fact, if you think about if you shift the experiment just a little bit to the left, they will resemble it almost exponentially more. Because again, you calculate R-squared value by finding the y difference between this. So just a subtle shift will cause a great effect on R. We also have an explanation for our error analysis, so analyzing our error. So the smaller peaks for our experiment may be due to some energy loss due to opposing forces that underestimated our theory, which, for example, could be caused by a somewhat uneven surface. So here is a similar demonstration of our radius versus time graph. Here is our theoretical graph, and here is our actual experimental graph. Next. You can see that this R-squared value is even lower, although it basically qualitatively agrees between the theoretical trend and empirical data. This may be changed, this radius versus time experiment may be a little low because there is a slower change in radius than we expected, which may be caused by an underestimation of friction in radial sliding. You also notice that the much smaller peaks than expected can also be explained by something we call an unstable buckling effect. So here is a video that shows what we found out about this phenomenon. So you see that when we twist the rubber band, sometimes it buckles into each other and it changes the radius of the thing. So we did some analysis into this. So we designed our own specific experiment to find to discover the buckling effect. So first, we have a ball hanging on the very rubber band that's rotating with the vertical reverse, so you can measure how long the rubber band is. And we hypothesized that the natural radius of the rubber band is a function of feet, which means that the more you turn the rubber band, the more it squeezes into itself. That means that when the rubber band is horizontal, we observe, from our experiment, we observe a buckling effect that would decrease the natural radius of the rubber band. Although it is not buckled, the twists only make the radius smaller but not drastically. Here we have a graph of natural radius versus angular change of the ball. This is for the blue you see is for the buckling, and the red is for no buckling. We also notice that the place, amount, and distance necessary vary for experimental trials. Note here that in the vertical system there will be no buckling effect because the gravitational force basically unbuckled the rubber band. However, there is some significant influence in the horizontal system where there is no force that stretches apart the buckling. I will also note here that gravity is taken into account over here because obviously if you're hanging on the ball over here, the gravity will also change the natural radius of the ball. But we already shifted our graph to account for this. But also we noticed that, curiously, the rubber bands that buckle actually do not cause a decrease in angular velocity in comparison to the rubber bands that do. We hypothesized that this may be because buckling creates some kind of linear outward force that originally not present. Also, the ratio of the masses between the rubber bands and the balls may be so small that the buckling effect has very little influence. So, less than a week ago, I found an article describing stabilities of rubber band that we think may be related to this. It is called conic stability. And basically, given some specific variables, we can find the stable regions and unstable regions. Here's our conclusion. The limits of our theory do short. First, we assume that static friction is negligible. We include the causation equations of motion and stochastic stabilities, which is basically about buckling. And here is our summary of our equations of motion. R dot theta dot phi dot. And here are angle and radius graphs theoretically. And here's our work cited. Thank you.
Okay.
Thank you for your very detailed presentation. I just have several clarification questions. So you said that you assume that the kappa and the always stay the same.
Sorry, assume what?
The kappa and the always stays the same for the length of the rubber band changes and when the angular displacement of the rubber band changes.
Actually, the K value will decrease if the rubber band is longer, and the torsion value will change accordingly.
Okay. And I'm still not sure what you mean by stability. Could you explain in which time the definition of stability?
Could you please go to the buckling video? Yeah, so when you twist it, it buckles. So that's what I call like an unstable buckling.
Also,
whereas if you just like twist it like this, it's not really.
So its tendency to buckle is how you define the stability. Okay. And did you change the number of turns for your experiments?
Yeah, we have a graph of our experiment 1 shows omega r versus n. So experiment 1 is slide 18 to 19. So slide 18. 19.
Okay, thank you. And can you go to page 10?
Okay.
There is radial motion of the balls, right?
Yeah.
So why is this here static friction force?
If you notice here, this is a radial, this is actually defined in our theta direction.
Also,
Yeah. So there might be a mistake on your part of reading the graph, but this is kinetic friction force.
so this is static. And what's the difference between this force and the rolling friction?
So basically, when the ball rolls without friction, rolls without slipping, it is incurring a static friction force, whereas where it is slipping is kinetic friction.
Also, it switches between the rolling and static friction for the period.
Actually, this may be a misunderstanding because I'm saying it slips in the r hat direction, but it rolls in the theta hat direction.
So, and the static friction, where does that come from?
So when you roll, there's static friction.
Also, it's like rolling friction. Okay.
Yeah.
Okay, is liberation time.
Good afternoon, dear judges and fellow competitors. I am the opponent for problem 11 following on electric band. So the overview of the report. Vacuum manifold also with an electric band that twists the electric band from on the table. They will begin to spin in one direction. And the common statement is that the motion will resemble that of a pendulum. So the thing with key points are what causes the motion of the pendulum, what are the relevant parameters, and what describes the period of its oscillation. And the overview of the report. For the reporter said that these balls are phenomenal. The balls rotate around each other, and also the distance between the balls changes. And for the theory, use the equation of motion in coordinates, and they have a couple of equations which was solved numerically with Python. And finally, they discussed the stability and buckling of the elastic band. And for their experiments, they use plans to control the turns of the balls, and they try different surfaces and different ball masses. Also, they try different effect of the angular displacement of the rubber band and its effect on the buckling. And here are the strengths and weaknesses of the report's presentation. They have a clear demonstration of phenomena, they have clear and concise graphs. They consider different parameters such as the mass and volume surface. They have quick time management, and that's why they have a well-structured report. But for the weaknesses, they did not consider the effect of the energy decay of the rubber band. And they did not discuss the conditions for the rotations, and also they did not include the effect of buckling on the spring constant. They did not change the note that, and they do not have video showing the phenomenon. So points to be discussed. For the theory, we would like to discuss what conditions will the phenomenon form, and the dependency of K and kappa on and the angular displacement, which the reporter very confidently stated that he has a well explanation for, and the energy decay of the elastic band. And finally, I will discuss something I observed on the formula for page 10. And for the experiments, I would like to refer the reporter to show me a longer video of the phenomenon, and also what the changes of page buckling has on phenomena and the deviations on page 23. So I would like to begin my discussion. So I would like to hear your explanation for how spin kappa changes when the length of the rubber band and the turns change.
So I think, as I mentioned earlier, if you have a longer rubber band, the K constant will decrease. This is actually very similar to a spring. For example, if you have a longer string, the K constant will decrease. And if you have two strings, a string that will decrease the length of the string, this K constant will increase.
But for example, you're saying that for a longer spring, the K constant will decrease for the longer rubber band.
Yeah.
And your explanation is that just like if you're attaching a spring to another spring, the K constant
This.
Oh, thank you. So you're saying that the K constant decreases just like how you're attaching springs in series?
It's not like that, but it has a similar effect.
Similar effect, but how do we compare that? I think these are two different things because when you scratch it, it may fatigue, but the force it takes to scratch the object may also increase, and it may also decrease. So I don't think the K constant decreases, necessarily decreases when you stretch it around that.
I agree that it is not one perfectly like spring, but we did conduct experiments that had longer rubber bands versus K constants. I don't think this is relevant to the policy statement itself. I cannot include that.
Okay. Do you have numerical data to show us? Can you model the phenomena materials buckling?
Actually, there is some degree of buckling in radius versus time graph. So, for example, on this slide, we think that we have some smaller peaks than expected, and we think that those smaller peaks can be because the rubber band is buckling.
And have you considered changing K, making K not a constant but a function in your simulation?
We can K not.
K changes with length because I think you can actually measure K just by thinking of mass on the
That's how we measured KS. I mentioned earlier. Unfortunately, we don't have I don't think we have an explicit kind of graph of K versus the length of it.
That's what you did a pretty good job. And does K change due to buckling? Because when you twist the rubber band, the distance between the ball actually shrinks. So that suggests that there is a force.
So I actually think that there will be a change because normally a rubber band is like this. Let's say it has a K constant of this. When it buckles, it becomes kind of like this. So actually the radius decreases. So I believe the K constant will actually increase.
Can you go to page 10? So this here is the origin, right? Yeah. And this is the force. Why do we add the origin to the force?
Because I'm trying to find the net torque on the ball.
So, but the torque, this is torque, or is this the force?
Sorry.
This is
Right. I understand what you're saying. You know what? I was practicing this explanation. I also got confused. Note how there's a radius of the ball over here.
Yes.
So you do know that torque is equal to R cross F. So
Yes.
basically, we multiply the radius over to the torque. So we have F is equal to torque over R. So that's why we have the torque.
So this is in the unit of forces, not torque.
Well, if you multiply this over, it's torque, but we multiply it over, so it's.
Oh, okay, thank you. Can you go to page 23? So, what's your explanation? The red line, is it red? Yeah, actually, what's your explanation for it lagging behind the blue line?
What's our explanation?
Yes.
We think that there may be some energy loss in the theta hat direction. If you go to page, we'll go to one of the experiments.
Energy loss in the theta hat direction.
So here we actually did an experiment to verify our rolling without slipping tests, and then we moved it to the right. So here is our very, very low friction PFA material. You can see that when we conduct experiments on that material, there's actually some friction in the theta hat direction,
Yes.
whereas our model assumes that there's no friction. But to be fair, all of them show rolling without friction. But we think that when there is some friction involved, that will cause the angle versus angle vacuum theoretical.
Some friction in the rolling country. So, the motion in the tangential direction does not split.
We assume in our model that it does not split.
Okay,
And
then
maybe there's a little bit of split.
Okay. Do you think there are conditions for this phenomenon to form? For example, if you were to conduct an experiment on a surface without any friction, then will it be able to oscillate?
Interestingly enough, this PFA material is the lowest friction substance in the world, and we use it. So interestingly, there's still a lot of rolling without friction. But another condition I would like to add as an additional insight is we talked about stability earlier, and another thing we noticed is that as the mass of the balls get really small, the buckling effect becomes really, really apparent. So this phenomenon can be occurring in that condition.
Wait, so how does this happen? Oh, because
This is, okay, so can I go to the booking side?
because there's not enough friction to hold the balls apart, the elastic band needs to be bubbles here.
No, so buckling is independent of what I'm trying to talk about. Okay? So this is another theory as to answer, but to add on to your question. So we think that when the rubber band buckles a lot, this phenomenon is cannot be demonstrated.
But how about the friction of the surface?
So the friction of the surface, we demonstrated that even in those friction forces, it seems to work.
Why do you think it still works when the friction force is very, very small?
I think the simple answer to that is that we observed it and it did work.
Okay, so you don't. What's your guess?
Guess as to why it works.
Yes. Why it rolls without slipping? Because there must be acceleration, and that must be provided by the frictional force.
I think it's because we
And
have
go to the previous
page.
where you with the friction from type
So actually, so you know friction is going to be equal to mu times n. So we hypothesized that even though the mu, so for example, the PFA, as you mentioned earlier, has a very low friction coefficient.
I think it's actually in your data is about 0.02.
0.13.
0.13. Okay.
This is the lowest friction. And we actually had some decent mass of our balls. So as I mentioned earlier, if the mass of the balls is really small, you observe some kind of buckling and inward sliding, all of that. So since the mass of our balls is large enough, I think that it concise.
So what's the mass of your ball?
I think we have a mass versus time. Should we go to that slide? They're around like 0.02 kg. That's one of the masses.
0.023. That is
100 grams? Yeah.
that is not like you said. What is 23 grams times the gravitational constant?
I think that's okay. First of all, the 23 grams is the largest one we have. But anyways, I think. But I think that friction force is enough to keep it rolling downstream.
Okay, and then I would like to move on to the discussion of energy decay of this elastic band. Do you think the elastic band, the energy decay from the elastic band is significant in this phenomenon?
Energy decay. I think it may be a variable that can be considered, but we use a variety of different bands. We tested that they are all the same, and we switched them.
Do you think there's energy decay?
I think there might be some, but I don't think it has a large effect. Since our radius versus time graphs are
Well, you don't have any experiments to confirm that. Do you have any idea how you could design an experiment to confirm or to test out the energy decay of the elastic band?
I would like you to offer me
Okay, yeah. I think you can use a torsional pendulum and use that.
Oh, interesting. We did experiment with the torsional constant pendulum to find the. Oh, sorry.
So if the oscillation looks like this, then the effect of the energy decay of the rubber band is significant. But if it looks like this, then the effect is negligible. So we think you can use this pretty easy experiment to determine the effect of the energy decay of the rubber band. Okay, and you have a long video showing your phenomenon.
Can go through. So I didn't include a long video because, as you could see, I was a little bit struck. I was like 10 seconds, a little bit over my 10-minute. But this is like a clip of our video.
Okay, so I would just like to confirm. In your experiment, you did not see how the central mass of the system did not move.
That is one of our assumptions. If you
Okay,
can go to page 6. We see here that there's no net horizontal force exerted on the system.
There's no net.
Net force. So remember there are horizontal forces, but they cancel out in the bad direction, which means that the center of mass of the system is assumed not to move.
Okay, and next question. How do you think this system will change when the rolling friction is very, very large? For example, if you put it on a very soft surface.
When the friction is very large.
The rolling friction.
The rolling friction is very large. So can you please go to experiment 3? So we conducted an experiment to verify our theory of this. We think that after a certain point, can I see politics or that?
This one.
So So we hypothesize that there's a boundary or at least a threshold mu, let's say if this is 0.3 and this is, let's say this is sliding with some rolling. And let's say we have mu equals 0.4. Let's say this is rolling without slipping.
Yes.
We hypothesize that this mu would be basically the same effect on the rolling without slipping as if this mu were 0.8. Because in both of these effects, the balls are rolling, so then the change in the friction will not, the frictional coefficient will not cause a difference.
But could it be like overdamped? Could it be when the rolling friction is really large, the system be overdamped? Yes or no?
Not in our observation.
Okay.
There is a
So in our discussion, talked about the physical phenomenon, and very interestingly, when the reporter said that for a really small friction, they were still able to observe the phenomenon. And we discussed the dependency of the thing, of the thing. And the reporter said that initially said that when the length increases, the pop-up decreases. We reached the conclusion that it doesn't necessarily decrease with the length. And the opponent, the reporter, didn't consider the energy scale of the elastic band, but they think that our suggestion for quantifying the energy scale of the elastic band would be a good experiment too. And we also clarified the addition of coordinate enforcement, so there's no problem with this equation. And the reporter was not able to provide me with a long video, so I couldn't discuss this placement of the center of mass. But the reporter said that they did not observe this. And also said that K change is due to buckling. And the deviation on page 103 may be explained by description.
deliver expression.
Because of the super low friction coefficient of the material that you use. So is that the reason why you didn't consider the technique?
Sorry?
Because of the friction coefficient of the material that you use in the experiment.
So could you please go to radius versus time graph, which is page 25. Yeah, so as you can see, this is, for example, a radius versus time graph, and you can see that it is damped. So we did, so our equations do show damping.
Okay. So the question for Robo and the reporter, did you think that the bone will change during the time and it is still the buckling is still small factor?
I think you said, well, buckling change over time. I think it will change over time because in that phenomenon, this demonstration in page, I think 5 or 6, I think it might be 5. Basically, you see that the radius increases and it decreases. The buckling effect is less apparent when the radius is long, whereas it is more apparent when the radius is short.
So did you model it?
Sorry?
Did you model it?
Oh, we did not model. We did have a model of buckling effect over here. So, but this is buckling effect as a function of B, which is this is buckling effect as a function of B, which is how much you turn the balls, instead of buckling effect with respect to R.
So what do you think?
You asked me, will the buckling effect change with respect to time?
Yes.
I think it will. And I agree with what the report has said.
So for the reporter, are you sure that the elastic figure fit your equation for the elasticity?
Sorry, what figure?
Equation.
So, for example, our angle versus time equation. These equations don't fit quantitatively. You can see the R squared value very well. But as we mentioned earlier, the R squared value isn't a really good way to measure this because it agrees pretty much qualitatively. And if you can see that a small shift in angle, as we discussed as a probability with the opponent, could cause this deviation. So I think they do agree.
Okay, so that's my question.
Okay, separation time.
Thank you. So the lawyer one, the review of the standard, and today my topic is go on the SUK. And for the reporter, we think the approach is clear formula, explanation, and easy understanding and completely data analysis, and good comparison of the variables. And the con is explain of the phenomenon and lack of forced explanation, and font was too small to see it clear. And for the opponent, the pros are clear understandable purpose of the question you asked, and a clear understanding of the structure of the report, and point on the key points, loss of the report, and clear understanding of detail of the experiment. And the cons are not enough suggestions for the better experiment, and didn't discuss deeper instead of asking questions. And the discussion between the opponent and the reporter. So the opponent asks, did you change your turn off meaning? And the response of the reporter says, yes, we did. And the opponent questions is that, have you considered K content as not a constant? Sorry, K is not a constant but a function in the experiment. So the response of the reporter says, we haven't. So in my opinion, we think the K is the key factors in the experiment. So we think the reporter should consider in the experiment. And the opponent asks, what's your explanation of decreased red line? So the response of the reporter says maybe there's some decreased energy. And the opponent asks, how about the friction in the experiment? And the response of the reporter says, our flow is smooth, so we think the friction is really small. And the opponent says, J, do you think there's energy decay? So the response of the reporter says, yes, we think there is an energy decay and maybe it's our improvement. Thank you.
Okay, reporter conclude remarks.
Okay, so thank you for listening. Here are my concluding remarks. First of all, I would like to clarify that I do in fact have an experiment correlation between the number of turns and omega r. So to go to the next slide. Here is our experiment that was omega r versus n. And also, with regards to the spring constant, this should be spring constant. We conducted an experiment where we found that a longer stretch rubber band will actually decrease K. So again, the torque equation on page 10 is actually verified and clarified in the report on that point. We believe that the experimental data, as asked by the reviewer, can lag a little behind the theoretical model because of some energy loss. We know that there is energy loss in the r hat direction, but there can also be some minimal slipping in the theta hat direction, which we didn't account for that comes off with the energy loss. And finally, I would like to say that I agree with the opponent that we can conduct an experiment to discuss and analyze the energy decay of the elastic band. Thank you.
Okay, question from Julie.
Okay, the reporter, you state that you have motion in three directions, right? The theta, the phi, and the r. You state that along the direction of r is slitting, but along the angular direction, the theta and phi, there is just pure rolling without slitting.
Yes.
Do you have any confirmation from the experiment?
Yes, we do. So, in fact, if you have, so here, so basically what this is our configuration of rolling without slipping. So,
What is this?
okay, so this is our the coefficient of friction of the ground and of the surface and the ball, and here is our rolling without slipping. So you can see that theoretically we would expect this and our data points match the theoretical line.
Here you say that if the friction is low, then there's a high rolling slitting rate. But isn't this contradictory to what we usually know? Because if there's no friction at all, then there won't be any rolling if it's just pure slitting.
Excuse me, I think I might have implied something incorrectly. We found in our experiments that even in very low friction surfaces, they actually somehow still do roll without slipping. We had a camera above, we have a ball, and we tracked the point on the dot to see whether it was rolling without slipping.
Yeah, but this experiment, actually, you just use one ball.
No, we used our system of two balls.
With two balls.
Yeah. So
But how do you tell that if it's rolling or not?
Okay.
I mean, experimental data, you observe.
So we have an overhead view of this system. So let's say we have our two balls connect over here. We mark the red dot on one of our balls. And we see by how much times the red dot appears because it is rolling in the phi direction, how much the rotation changes. And we also noted how much the ball moves with respect to this. So if we note that the number of times this turns, so that would be 2 pi r of this, matches extremely closely to the distance it travels, then that is how we verify that it rolls without slipping.
You go to a slide of the comparison between experiments and theory. R squared equals 0.7. Yeah, it seems that for the experimental curve, the T ratio seems lower. So if you compare the theoretical curve and the experimental curve, yeah, it seems not only shift a little bit, but the period is longer.
Yeah.
Can you comment that which parameters could cause this longer duration?
So if this is experimental graph, it is longer, that will indicate that the angle is changing slower with respect to time, which will indicate that perhaps there is a little bit of slipping as you go through time. Because, or that could also indicate energy loss in the rubber band as I discussed with the opponent.
Okay, how about your opinion?
In my discussion, after we saw this graph, we went to the previous graph of the rolling of the slipping. So I think without experimental data, I cannot conclude if it is primarily the energy loss due to the rubber band or the unevenness of the graph. But I think the unevenness of the graph has a larger effect, the energy loss in the tangential direction.
Do you have any comment?
So can you repeat your?
Oh, so for the experimental curve, that is ray curve. It seems that the oscillation duration is longer. So, yeah, any comment about which parameter might lengthen the duration?
I agree with the report.
Okay.
I have one short question for you guys. Just look at the peak, you can see the damping decrease, right? That means the energy dissipation. And you also do some modeling. So how can you get the coefficient for the amplitude? Okay. Some coefficient.
So
What is harmonic oscillation problem?
yeah, so I'm not sure how specifically analytically that will work.
But in theory, you have the damping theory, right?
Yeah, I think it is because the angle is actually coupled with the radius, and since there is some force in the radius direction, and that's coupled with the angle, that will also help contribute to the angle.
Since he has the damping theory, he can simply plot the function for the oscillation and finds the one with the best, that matches the best, and take its B value, take its damping value.
Okay. So for the
So I say the opponent says I agree with that.
Any now the score time. Okay, for the reporter, 9, 7, 7, 6, 9. For the opponent, 9, 7, 9, and 7. For the reviewer, 8, 7, 5, 6, 5, 4. Okay, we end this section.